Welcome to the sixth session of BSc Physics. The topic of discussion is atomic physics. In this session, we are going to discuss the second feature of the vector atom model, that is the spinning electron. The contents of this session are the spinning electron, and secondly, the using of both space quantization, idea of space quantization, and the knowledge of spinning electron to define the different quantum numbers. Coming to the spinning electron, the three quantum numbers, the principal quantum number n, the orbital quantum number L, and the magnetic orbital quantum number ml, describe the electron as a particle with 3 degrees of freedom. But experiments showed that the electron has an internal degree of freedom, that is the 4th degree of freedom, due to its spin, resulting in an associated angular momentum called spin angular momentum. As fine structure cannot be explained adequately with the three quantum numbers n, L, and ml, Ullhenbeck and Goudsmit proposed the hypothesis of the electron spin. According to them, the spin of the electron is similar to the spinning of a planet about its own axis as it moves in an elliptical orbit around the sun. According to the quantum theory, the spin motion, like the orbital motion, is to be quantized, and a new quantum number called the magnetic spin quantum number, as denoted by ms, has to be introduced. The spin angular momentum has a value of h by 2 pi. Hence, due to its spin, the electron has an associated spin magnetic moment mu s. This spin magnetic moment can either be parallel or anti-parallel, depending upon the directions of spin with reference to the surrounding magnetic field. These two spin states are described by the spin quantum numbers S equals plus or minus half. Either it can be plus half or it can be minus half, depending upon its direction of spin. Therefore, the spin angular momentum of an electron, which is a vector, is Ps, is given by S into h divided by 2 pi. Since S can take value of plus half, we get the spin angular momentum as equal to h divided by 4 pi. The gyromagnetic ratio for spin motion, which is different from orbital motion, can be written as mu s divided by ps, which is equal to gs into E divided by 2 times ME. It is assumed that GS is equal to 2 in agreement with experimental results. Substituting this value in the above expression, we get mu s equals 2 into E divided by 2 times ME into PS, which is equal to E divided by ME into H divided by 4 pi. Finally, we can write as EH by 4 pi ME. The right-hand side of this expression is a familiar expression for Bohr magneton. Therefore, mu s is said to be equal to mu b. Thus, the spin magnetic moment of the electron is equal to the Bohr magneton. Hence, according to quantum mechanics, the orbital angular momentum of the electron is PL equals root of L into L plus 1 into H divided by 2 pi, where L, which is the orbital quantum number, we can take integer values starting from 0 as 0, 1, 2, 3, etc. up to n minus 1. Now this quantum number is also referred to as the azimuthal quantum number. Similarly, on the same lines, the spin angular momentum of the electron is given by PS equals root of S into S plus 1 into H divided by 2 pi, where S is said to be equal to half. Coming to the idea of different quantum numbers. The location of the electron relative to the nucleus and the energy associated with it is described by a set of 4 quantum numbers. Among them, the first one is the total or principal quantum number, n. Here, n can take integer values starting from 1 as 1, 2, 3, etc. Here, the integral values exclude 0. The corresponding orbits for n equal to 1, 2, 3 are called k, L, m, n, etc. The second quantum number is the orbital or azimuthal quantum number, L. The values of azimuthal quantum number, small l, are 0, 1, 2, 3, etc. up to n minus 1. That means it can take any integral value. It defines, the value of L defines the shape of the orbital, and the orbital angular momentum for n equals 1 is L can have only one value. For n equals 2, L can have two values, that is 0, 1. For n equals 3, L can have three values, that is 0, 1, 2. And the value of L represents the presence of subshells S, comma P, comma D, comma F, etc. The third quantum number is the magnetic orbital quantum number, ML. Here ML can take the values 0, comma plus or minus 1, comma plus or minus 2, comma plus or minus 3, etc. up to plus or minus L. Or in general, it can take 2L plus 1 values ranging from minus L to plus L. ML represents orientation of the electron in an external magnetic field, and also it accounts for the splitting of spectral lines in presence of magnetic field. Next is the fourth quantum number, that is magnetic spin quantum number, MS. Here MS can take two values, that is minus half and plus half. Minus half corresponds to anti-parallel and plus half corresponds to parallel with respect to the applied magnetic field. MS represents orientation of electron spin relative to the same frame of reference. The difference in spin quantum number for two electrons in any orbit is half minus of minus half, which is equal to plus 1. Coming to the last quantum number, that is the quantum number related to spin orbital interaction, which is called as the total angular momentum quantum number, represented by small g. Here, each electron in an atom has a certain orbital angular momentum represented by small l and a certain spin angular momentum identified by s. Both these quantum numbers contribute to the total angular momentum J of the atom. That is, J is equal to L plus S. J is quantized in both magnitude and direction as Pj is equal to square root of J into J plus 1 into h by 2 pi, where small j is equal to L plus S, which is equal to L plus R minus half, since S can be either plus half or minus half. For a single electron, S is equal to half. The orientation of the spin can be in any one of the directions. Hence, J is equal to L plus half, or L plus half, or L minus half, corresponding to parallel or anti-parallel of S with L. Thus, the method of obtaining the resultant angular momentum of an atom by the vector addition of the orbital and spin angular momenta of the electron is known as vector model of the atom. Thank you.